This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will cover the insert method of binary search trees. As we do that, we will also conduct its time complexity analysis. Let's get started. To make sure that we're on the same page, I need to clarify on some assumptions that I have. First, we have set up the implementation of the node class to represent each node in a binary search tree. Each node has a value and two references leading to two different other nodes, the left and the right children. For simplicity, a node only deals with integers. Second, based on the implementation of the node class, we have also set up the skeleton of a class representing a binary search tree. And there's the search, insert, and the delete methods. We implemented the search method in the last video, and the insert method is what we are going to implement now. Third, imagine that we already have a binary search tree example that looks like this on the left side of the screen. With these three assumptions set, we are ready to discuss the insert method. What steps are involved in inserting a new node in a binary search tree? Same as the search method, you start with the root node. Second, you search for the correct position based on the given target value. This process is similar as what you will do in a search method. If the target value is smaller than the current node value, you would move to the left subtree. If bigger, you will move to the right subtree. If the same, you will silently stop. Just to be sure, we are assuming that the binary search tree doesn't allow any duplicate values. Last, when you reach to a position that is null, you will insert the new node at the null position. Let's apply these steps to an example to get a better understanding of what happens for the insert method. You have a binary search tree example on your left, and we are going to insert the value of 35 into this tree. We will start with the root node. After comparing the root node value 50 to 35, you see that the target is smaller, so you move to the left subtree, like this. You will do the same to the node of 31 now. The target value 35 is bigger, so you move to the right subtree of 31, like this. The next node is 41. The target value 35 is smaller, so you move to the left subtree, like this. The next node is 32. Well, the target value is 35 and bigger, so you would move to the right subtree, like this. The next node is 34. The target value 35 is bigger, so you would move to the right subtree, like this. The next node is 36. The target value 35 is smaller than 36, so you would move to its left subtree. However, the node 36 doesn't have a left subtree, which means that the current position is null, and the right position for this new node of 35. So you will add the node of 35 to this position, like this. That's the full process of how you insert a new node into a binary search tree based on these given steps. Translating these steps to pseudocode, you will have this. As you can see, we are doing some overloading methods in the pseudocode again, just like in the search function. The two functions come with the same name but different parameters. The first function is the one that's exposed to users, while the second one is hidden from the users but does the heavy lifting behind the scene. This setup is user-friendly and makes it easy for the implementation. Since the second function does the actual work, so let's focus on it. This function takes two parameters, one representing the current node being compared to the target, while the other representing the target value. This function always returns a node to maintain the proper tree structure. If the current node is null, that means you have reached the right spot to insert a new node with a target value, so a new node with the target value will be returned. If the current node is not null, and its value is bigger than the target, it will call the insert function recursively on its left subtree and assign the function to the dot-left reference of the current node. Otherwise, it will call the insert function recursively on its right subtree and assign the function to the dot-right reference of the current node. In both cases, it will return the same node as is given in the parameters. Let's talk about its time complexity. So, what would be the worst case scenario, and what time complexity would that be? If you are forced to compare every node in a binary search tree to the target value, you have a worst case, like this. When you finish comparing every node value to the target, 35 will be inserted into the end of the binary search tree, like this. If a binary search tree contains n nodes, you need to compare every node value to the target, and each comparison takes constant time. Then, the time complexity will be linear time, expressed as Tn belongs to big O of n. That's the worst case. What about the best case? The best case scenario is when the insertion is finished in a single step, like the example that you see on the left side. When the given target value is 52, then it only takes a single step for you to insert the node with its value into this tree. When the given target value is 52, it only takes a single step to insert a new node with this value into this tree as the right child of the node of 50, like this. The insertion is finished in a single step of comparison, and it takes constant time to do so. As a result, the time complexity is big O of 1. Both the time complexity of the worst and best case of the insert function are the same as the search function. What about the average case? The analysis of the average case of the insert method is actually also the same as that of the insert method. In short, time complexity Tn of the average case is in proportion to the comparison numbers. To account for randomness, we need the help from expected value. The assumption of computing the expected value is the same as that of the successful search. Based on the assumption, we will be able to compute the recurrence relation for the expected comparison numbers. On the right side of the equation, 1 is the number of comparisons required at the root level, and the summation is the expected number of the comparison in the next step. I divided by n multiplied by C of I represents the expected number of comparisons when the insert goes into the left subtree, while the other item represents the expected number of comparisons when the insert goes into the right subtree. With the recurrence relation, we can deduce the formula of C of n independent from the random variable. Again, the deduction process is the same as that of the search method. It involves using the assumption of a balanced tree and what you learned from calculus, such as differential equation and how to exponentiate both sides of a formula. We will be able to deduce that the expected comparison number is log n, because the time complexity is in proportion to that of the comparison number, so it runs on log n time. That's the average case for the insert method. Now you understand everything about the insert method. In the next video, we'll dive into another basic operation of the binary search tree, which is the delete method.